Hey, Math and Science Academy. Today we're talking about Coulomb's law, and this equation is kind of setting up a relationship between how charge and distance affect the amount of force that two electrostatically charged objects are going to have towards each other. So if we were going to say the equation in words, we would say the electric force between two objects equals Coulomb's constant times the charge on one times the charge on the other divided by the distance between them squared. Okay, so we've talked about electric forces such as attraction. This is what attraction looks like. We have this negatively charged particle that is going towards the positively charged particle. We have repulsion, which is where two like-charged things are pushing apart so that their electric fields can be balanced all on their own. And so the inverse square law describes relationships. It describes cause and effect, and it's talking about when one thing happens, how is another affected? When we're talking about inverse and direct relationships, what we're looking at is scientists modifying a set of conditions to see if there's a pattern behavior in another set of measurable quantities. So this is true whether it's biology, whether this is math, whether this is sociology. This is something that you can see in like multiple fields. It's just a way of describing relationships. When one thing goes up, the other thing goes down. Or when one thing goes up, does the other thing go up? How does a change in a set of variables or conditions causally affect an observable outcome? So let's look at some of these things here. In physics, we're interested in relationships like this. How does a force affect acceleration of an object? Well, when a force increases, then the acceleration also increases. That's a direct relationship. How does the speed of a falling object affect the amount of air resistance it experiences? Well, if the speed of a falling object increases, then the air resistance is also going to increase. How does the distance from a page to a light bulb affect the amount of light that illuminates the paper? This is one where if the distance between the bulb and the page increases, the illumination is going to decrease, right? There will be less light on that paper. How does the frequency of a sound wave affect the speed of a wave? That's a good question. If the frequency of a wave increases, then the speed of the wave, I believe, is going to decrease. And how does the distance between two charged objects affect the force of attraction or repulsion they encounter? If the distance between the charged objects increases, then the force of attraction or repulsion they encounter is going to decrease. More distance, the less they're going to interact with each other. And you guys saw this in simulations that we looked at earlier, where the farther apart they are, the shorter those force lines are, right? And the closer together they are, the longer those force lines are. If they're close together, they really want to be together, or they really want to be apart. So a basic inverse square relationship is like this. I apologize for the blurry graphic here. But force is about equal to 1 over the distance squared. That's what an inverse relationship is mathematically. So Coulomb's law says that force has an inverse relationship to distance. When distance goes up, force goes down. When distance goes down, force is going to go up. So here we have in the equation, we have the electric force, which is how much attraction or repulsion is going on. And force and distance have an inverse relationship. R means the radius between those 2 point charges. So like just coming up from the center of that point charge to the other one, how big is that radius squared? Because it has like that much of a magnitude of effect on the force there. So charge also has an effect on the force, but it has a direct relationship. The more charge, the more force. The more force, the more charge. So then we can add on to this Coulomb's constant. Coulomb's constant is kind of what holds it all together. It is just a giant number, 9 times 10 to the 9th newtons times meters squared times Coulomb squared. Distance, charge, force is what all of those units are in there. Okay. So force has a direct relationship to the amount of charge on the objects. If the charge goes up, the force goes up. Okay. So inverse relationships in electrostatics, so distance is an inverse relationship when it comes to electrostatic forces. The more distance there is, the less force there's going to be. The less distance there is, the more force there's going to be. It works like a teeter-totter, just like that. Increasing the separation distance decreases the force of attraction. Decreasing the separation distance increases the force of attraction. So what does it mean that they have an inverse square relationship? That means that the electrostatic force between 2 point charges varies inversely with the square of the distance of the separation between the two charges. So if the separation distance is doubled, increased by a factor of 2, then the electrostatic force is decreased by a factor of 4, like 2 raised to the second power. And if separation distance is tripled, which is increased by a factor of 3, the electrostatic force is decreased by a factor of 9, 3 raised to the second power. So the square effect makes the distance of double importance in its impact upon electrostatic force. So to show what that means, it's one thing to look at the words of it, but this is what it means like effectively. So thinking about that, the thing we were talking about earlier with if you have a page illuminated by a light source, the closer that you are, there's like way more light on that page, right? So like if you are this far away from the light source, then there will be this much light on your page. But if you're this far away, all of that light is actually spread into an area that is 2 squared. So it's really like this amount of light is spread over 4 spaces. So it's like you're getting like 25% of the light that you would have gotten. And then here, if you are 3 units away, then that same amount of light is spread over 9 or 3 squared spaces here. So yeah, 3 squared. So this amount of light is just, it's like 1/9 of what it would have been before. So here's another way of looking at that. Pretty bright, less bright, much less bright, because all of that energy is spread over such a big distance. And here's another way of looking at it when it comes to charge. So if we're talking about point charges, then this is like 0, right? This is where it starts. This is a distance of 1. So then that charge is spread out over, 4 of those spaces. And then if we go farther, that charge is spread out over 9 of those spaces. So you can see how that inverse square relationship works there. So point charges, basically this is kind of like some information just kind of like to talk about what these things are. A sphere acts as a point charge with its excess charge located at its center. So if you're talking about, like if you're looking at the charge on one atom, that charge comes from the very center of it and goes outward there. As opposed to, like for instance, parallel plate capacitors, which have a uniform electric field that's more of like positive, negative, straight down. Point charges are more like circular points. So then Coulomb's constant is a proportionality constant. It kind of holds everything together. And something that's interesting here is that you'll notice that the units on this, newtons, meters squared, Coulomb squared, they cancel out everything else so that you can just look at like the meters squared and the charge squared are the units on the distance and charges on the amount of charge. So you end up with just newtons left over, and that's what makes this whole equation work. So there is some practice problems for you to work on, both in the Coulomb's law Google form, and then if you want to practice before that, in class we did this where you clicked on this link and went to the Coulomb's force concept builder from the physicsclassroom.com. So yeah, you can go there, physicsclassroom.com, thephysicsclassroom.com, search for Coulomb's law concept builder, or if you have this slideshow, you can click on the link. And I will leave you with that.